So in this clip we're thinking about focusing. How does the eye ensure that the image that is formed in the retina is in sharp focus? Well, we have the cornea at the front, as we know, and then we have the lens. Now actually 75% of the refraction of the light rays that goes into the eye is achieved by the cornea. Now what we mean by this refraction is that the light rays will come in, but then they need to be bent through a particular angle to focus them on the retina. And that angle through which the light rays are bent is the refraction. So about 75% of the refraction will take place in the cornea, the other 25% in the lens, which doesn't sound like a lot, but the thing is, the lens is the bit that is flexible. The refractive index of the cornea is constant. So we need the ciliary body and muscles, which are just here. And the lens is suspended by these suspensory ligaments made up of the zonular fibres. Now to see what's happening, we need to look at this from the front. So if we're viewing this from the front, if we're viewing this in this direction here, then what we actually have is there is a ring of ciliary muscles comprising the ciliary body. So this is a complete ring, because remember the eyeball is spherical. So there's a ring there. And the size of this ciliary ring can vary because the muscles can contract and they can relax. And the lens is going to be in the middle here. So this is the ciliary ring here, ciliary body. The lens is in there, and we have the suspensory fibres holding the lens, the suspensory fibres holding the lens in this ring of ciliary muscles. So what we've drawn there in red is the suspensory ligaments, the zonular fibres. So that's looking at it from the front. Now for the process of accommodation, the ciliary muscles can relax and they can contract. Now to look at objects close up, and young adults can look at objects that are only about 10 centimetres away and still focus. This is actually controlled by the nervous system, so impulses come from the oculomotor nerve. And what will happen is, here we have the outside of the ring of ciliary muscles. And to focus on close-up objects, there's going to be contraction of the ciliary muscles. And when the muscles contract, that's going to reduce the size of the gap in the middle. It's going to increase the diameter of this ring here, or the thickness of this ring. It moves in like this. And we had the suspensory ligaments, but because now the ring has moved in, there's less pressure on the suspensory ligaments. So these are now loose. And when the lens can, the elasticity of the lens will make the lens go short and fat. So the lens will go short and fat if it can. So the lens will become shorter, or it will have a less diameter, a more narrow diameter will become thicker. And that's important because when the lens is, if we have like a short fat lens here, like this, and we have a short fat lens, then what will happen when the light rays come in? Light rays will be actually refracted at the surfaces of the lens, but when that comes in, it's going to change the angle quite significantly. So it will change the angle. So this angle here is greater when the lens is short and fat. But if the lens is thin, the lens is stretched, still the same volume of lens here, but now it's stretched. So the light will not be refracted as much, the angle of refraction will be less. So short fat lens, high angle of refraction, the light rays are bent a lot. Thin lens, lower angle of refraction, the light rays are not bent as much. So to focus on close objects, the ciliary muscles contract. That relaxes the suspensory ligaments, and when the lens can, it will naturally become short and fat. The elasticity of the lens naturally makes it shorter and fatter, increasing its refractive index. And that's important because light rays from a close object are still going to be diverging, going apart. So they need to be converged more to focus them on the retina. So, short close focusing, contraction of the ciliary muscles. Contraction of the ciliary muscles means the ciliary ring gets broader. That reduces the tension on the suspensory ligaments. So they no longer stretch the lens. So the lens contracts with its own elasticity and becomes shorter and fatter. So this increases the refractive angle. So there's more convergence of light rays for focusing and accommodation. But we also need to focus on distant objects. So for distant focusing, what will happen for distant focusing is that the ciliary muscles will relax. So here we have the same size external ring of ciliary muscles. So remember, this one was near focusing, and this one is distance. Now what happens is the ciliary muscles relax, and when the ciliary muscles relax, the ciliary ring gets shorter, thinner. So contraction of the ciliary muscles makes the ring thicker. Relaxation of the ciliary muscles makes the ring thinner. But of course, the zonular fibres now, because the ciliary muscles have moved out, these are going to be stretched. So the suspensory ligaments are stretched. And of course the lens is in the middle here, connected to these suspensory ligaments. So that means the lens is going to be stretched. And when the lens is stretched, stretching of the lens is going to increase the diameter, so the lens is going to become thinner, like this. That means the light rays are going to be refracted less. Because when light is coming from 6 meters away or more, the light rays are almost parallel. From distant objects, the light rays are essentially parallel. So that means they don't need to be bent as much to focus on the retina. So from close objects, the light rays are still diverging, so they need to be refracted more. So we need the shorter, fatter lens. But for distant objects, we need less refractive angle. Most of it's going to be supplied by the cornea anyway, so the lens, we need less refractive angle. So the lens is going to become thinner because the ciliary muscles have relaxed. So distance vision, the ciliary muscles relax, the ciliary ring becomes thinner, thereby stretching the lens. That reduces the refractive angle of the light passing through the lens. Less refractive angle, so the almost parallel light rays from more distant objects don't need to be refracted as much, and they will also be accurately focused on the retina to give us accurate focused images at a distance. So active ciliary muscle contraction for close focusing, but for distance focusing the ciliary muscles just need to relax, but that stretches the lens. The lens gets bigger because it's thinner, stretched and thinner, so the refractive angle is less. So for moving from close to distant objects, we have the coordinated activity of the ciliary body, the ciliary muscles, the zonular fibres, altering the refractive index of the lens.